Well, so the point is actually you cannot always invert a matrix. Okay? So recall we've seen this formula that A inverse is 1 over determinant of A times the adjoint matrix. And, well, we've learned how to compute this thing. Remember, we had to take minors, then flip some signs, and then transpose. Well, that step we can always do. We can always do these calculations. But then at the end, we have to divide by the determinant. Well, that's fine if the determinant is not 0. But if the determinant is 0, then certainly we cannot do that. So, in fact, what I didn't mention last time is that the matrix is invertible. That means it has an inverse exactly when its determinant is not 0. Okay, so that's something we should remember. So if the determinant is not 0, then we can use our method to find the inverse, and then we can solve using this method. If not, then not. Yes?
Sorry, can you explain that? Like you can invert A if the determinant of A does not equal 0?
That's correct. So what I'm saying is we can invert the matrix A if the determinant is not 0. And if you look again at the method that we saw last time, so first we had to compute this adjoint matrix. And these operations we can always do. If we are given a 3 by 3 matrix, we can always compute the adjoint. And then the last step to find the inverse was to divide by the determinant. And that we can only do if the determinant is not 0. So if we have a matrix whose determinant is not 0, then we know how to find the inverse. If the determinant is 0, then of course this method doesn't work. But I'm saying actually even more, there isn't an inverse at all. It's not just that our method fails. I cannot take the inverse of a matrix with determinant 0. And geometrically, well, precisely the situation where the determinant is not 0 is exactly this nice, usual situation where the three planes intersect in a point. While the situation where the determinant is 0 is this situation here, where the line determined by the first two planes is parallel to the third plane. Okay? So let me emphasize this again. And let's see again what happens. Okay, so let's start with an easier case. So it's called the case of a homogeneous system. It's called homogeneous because it's the situation where the equations are invariant under scaling. So a homogeneous system is one where the right-hand side is 0. Okay? There's no b. If you want, the constant terms here are all zeros. 0, 0, 0. Okay, so this one is not homogeneous. So let's see what happens there. Well, so what that means, so let's take an example. Instead of this guy, we could take x plus z equals 0, x plus y equals 0, and x plus 2y plus 3z also equals 0. Well, can we solve these equations? Yeah, I think actually you already know a very simple solution to these equations. Yeah, you can just take x, y, and z all to be 0. So there's always an obvious solution namely 0, 0, 0. And in mathematical jargon, this is called the trivial solution. Okay? So there's always this trivial solution. And what's the geometric interpretation? Well, having zeros here means that all three planes pass through the origin. So certainly the origin is always a solution. the origin is always a solution because the free planes pass through the origin. Okay. So now there's two subcases. Okay. One case is if the determinant of the matrix A is non-zero. Well, that means that we can invert A. So if we can invert A, then that means we can solve the system by multiplying by A inverse. If we multiply by A inverse, well, we'll get x equals A inverse times 0, which is 0. Okay, and that's the only solution. Because, well, you know, if ax is 0, then let's multiply by A inverse. We get A inverse ax, that's x, equals A inverse 0, that's 0. We get x equals 0. We've solved it. Okay, no other solution. So, to go back to these pictures that we all enjoy, it's this case. Okay. Now, the other case, if the determinant of A equals 0, then it means that actually this doesn't quite work. So let's see. What does it mean that the determinant of A is 0? Well, remember, the entries in A, they are the coefficients in the equations. Okay? But now the coefficients in the equations, they're exactly the normal vectors to the planes. So that's the same thing as saying that the determinant of the three normal vectors to our free planes is 0. So that means that n1, n2, and n3 are actually in the same plane. It's called coplanar. Okay? These three vectors are coplanar.